Brasileiro de Geotecnia, realizado na cidade de Coimbra, em Portugal. A conferência foi proferida pelo professor John Burlan, por sua notória contribuição à engenharia e a sua amizade de muitos anos com o professor Victor. A segunda edição será proferida hoje. Com a palavra, convidamos para que suba ao palco o coordenador da sessão, o professor Jarbas Milititsky.
Boa tarde a todos. É com imensa satisfação que nós realizaremos agora a segunda de Mello Lecture. Eu gostaria de convidar para fazer parte da mesa a presidente da Sociedade Portuguesa de Geotecnia, doutora Laura Caldeira. I'd like to invite the President of the International Society of Sound Mechanics, Jean-Louis Briot, to come to the table. I'd like to invite Professor John Barton to join us on the table. And finally, I'd like to invite the speaker of the night to join us on the table, Professor Poulos.
I met Professor de Mello in 1985 as a young professor. It was in San Francisco at the International Conference. I introduced myself, and he was kind enough to talk to me for a while. I listened to some of his presentation, and there is no doubt in my mind that he was a giant in our field. And while he's no longer with us, his contributions will impact many generations to come. I want to leave you with a thought that comes to my mind when I think of Victor de Mello. Indeed, he was always jovial. I always saw him with a smile on his face. So I would like to leave you with this thought, which was very likely a part of Victor's philosophy: happiness is a choice. Now, this is a tie which I wish I could have given to Professor de Mello. It is a tie that symbolizes the cooperation between countries, that symbolizes his work in ISMGE. Since I cannot give it to him, I'll do the next best thing. I'll give it to his son, my friend, Louis de Mello. Louis, please come.
Eu gostaria então de passar a palavra ao professor John Barton.
Thank you very much indeed, Mr. President. It's a great honour to be invited to summarise the first Victor de Mello lecture and to introduce our lecturer for the second Victor de Mello lecture. I've been asked to present a 15-minute summary of the first Victor de Mello lecture, which I gave in Coimbra on the 7th of April 2008. And I have to say that to condense a 1.5-hour lecture into 15 minutes is quite a challenge. But I will just attempt to highlight a few of the key points of that lecture. The full lecture was published in Soils and Rocks, volume 31, and you can find it on the internet. Now, because it was the inaugural Victor de Mello lecture, I felt that it would be appropriate to attempt to capture something of Victor the person and Victor the engineer. It's really for succeeding lecturers to evaluate his engineering contributions, and I'm sure that will go on for some time. The title of the lecture was Reflections. Now that word means the throwing back of images. And what I did was to attempt to share some of the images of this really remarkable man. So this brief 15-minute condensation of the lecture is really a reflection of a reflection. Some of the pictures that I'm going to show, which include Victor, actually don't relate to the particular event that I'll be talking about, but I think they do reflect Victor and his approach and his personality. So I want to talk first of all about my first meeting with Victor. And I told his daughter Lucia that she would be having a surprise this evening, and there she is with Victor and with Maria Luisa. Now, I first met Victor and Maria Luisa de Mello in Swaziland on a pre-conference tour prior to the 6th African Regional Conference in Durban. And they flew into the capital of Swaziland, Mbabane, and joined the rest of the party. We were relaxing around a swimming bath at the Holiday Inn when Victor and Maria Luisa arrived. They were both wearing large, floppy sun hats. And then immediately, the whole atmosphere became vibrant. There was non-stop conversation, and we laughed, and we joked, and believe it or not, we even sang. It wasn't that Victor and Maria Luisa took us over. They actually galvanized us, and we were all drawn together into a new experience, an experience that I described later as living in a state of heightened intensity. During the next 2 days, we drove southwest from Mbabane to Durban, visiting a number of civil engineering projects on the way. And at each site, Victor subjected the engineer in charge, as indeed he is in this picture, subjected to the engineer in charge to an intense interrogation, not just in relation to the technicalities of the scheme, but the economic and social aspects of it as well. It was done with good humour, but with an obvious breadth of experience and a remarkably quick and incisive mind. And in between, during our bus journey towards Durban, and in the evenings, our conversations ranged widely over almost every conceivable subject. I remember one conversation with Victor in particular, in which he expressed concern about the dangers of developing countries relying on the advice of experts imported from the developed world. That's a theme that we return to frequently in his lectures, and referring to the classical story of the siege of Troy by the Greeks, he would use the phrase, "Beware the Greeks bearing gifts." A modern adaptation of that phrase, when you are being offered computer software, is "Beware of geeks bearing gifts." Now, at the conference, and Luis Guillermo will be pleased to see this picture, at the conference I was able to watch Victor in action at close quarters. And as a panelist, I think he's chairing that particular meeting, but as a panelist, I observed that Victor loved debate and would go out of his way to seek debate. Now that could be upsetting to some, but I saw very early on that Victor was quite prepared to revise his views in the light of the debate, even though he appeared quite often to be aggressive and quite argumentative. Now, the title of his address to the 6th African Conference was Some Lessons from Unsuspected, Real and Fictitious Problems in Earth Dam Engineering in Brazil. He described the evolution of his experiences in the design and construction of over 50 major earth dams in Brazil and elsewhere in Latin America, using residual soils and saprolites in particular. I can strongly recommend that paper to you. It is well worthwhile reading. And in that lecture, he gave a number of warnings. He warned of the grave dangers and the distortions that can result if a specialization is permitted to drive the project. The overall balance and coherence of the project needs to be maintained, with each specialization playing its part. And excessive domination of specializations can also obscure the chain of responsibility. And that is a very serious matter indeed. And once again, during that lecture, he warned of the grave dangers of importing technical know-how from Western temperate zones to geological settings which are outside the expertise and experience of the experts. And he called it, this is typically de Mello, he called it the import of technical don't know how. And during the opening remarks of that lecture, he reminded the audience that we should never forget the primordial precedence of values. Human being first, engineer second, specialist third. And this is what he wrote. But I am compelled to state, right from the start, that in my experience, it is principally in the connection between soil mechanics and the overall field of civil engineering, and in our obligations as members of society, that the greatest challenge and the chances of creative vision beckon us and lead us forward. Now, I would say that that is rather typical of Victor de Mello's writing. And I had the honour and pleasure of co-authoring with Victor the 1977 Tokyo State-of-the-Art report on the behaviour of foundations and structure. And in so doing, I quickly learned a lot about Victor's approach to writing. So when you're puzzling over his writing, the important thing is to understand that Victor painted word pictures, and he loved word play. I remember attending a lecture of his in Brazil when he was speaking in Portuguese, and the translator broke down in the middle of his presentation and explained that she could not translate what he was saying, and I quote, because he was playing with words. And I do hope that the translator working on my words does not break down trying to interpret them. So here are some examples of Victor's word play. We need not look for new tasks, but merely look at tasks newly. Another one. I may be described as specializing in being a practicing generalist. Water has an unfortunate habit of seeping through every theory, and one that you love is choose your love and love your choice. Now, I think the way to understand a picture is not to examine each brushstroke in detail, but to stand back, perhaps half close your eyes, and then take in the whole picture. And this approach is particularly true of the flamboyant and zestful Impressionist paintings. So let's look at a well-known picture. In this slide, I think we see some dark, incomprehensible patches. And maybe you've read some of Victor's writings and wondered about the comprehensibility of what you're reading. If you stand back a little bit, you then see some flashes of light and colour. And I think we can see possibly that the sea is emerging in that picture. So let's stand back a little more and look at the full picture. And we see that it is full of meaning, full of motion, and full of light. It's a well-known picture which was contemporary with the event of the escape of Rochford, but I won't go into that. But I learnt myself that this is the way to understand and read Victor's writings. You need to savour his figures of speech, his wordplay, his zest, and try to absorb a whole paragraph or even a whole section at a time. Now I want to refer briefly to Victor de Mello's ranking lecture. So here is the poster, which was on display at Imperial College, Reflections on Design Decisions of Practical Significance to Embankment Dams. And here is a picture of the Great Hall at Imperial College, just before the lecture was given. And you see at the front right-hand end, Professor Peter Vaughan, and then next to him, I think it's Victor himself, with Professor Noel Simons talking to them. And then further to the left, we have Noel Simons' wife and Mrs. Joyce Penman sitting next to each other, and Maria Louisa over towards the left, sitting next to my wife Jill, who is sitting next to a very young Professor Irwin. Now, in the first few pages of the published paper, if you read it, you will find that there really is an illuminating and thought-provoking treatise on the fundamental principles of engineering design. And certainly the start of that main lecture is really worthwhile close study and discussion. Characteristically, Victor started his lecture by referring to a Roman legend. During the long-running war between Rome and Alba Longa, it was agreed that settlement of the war would depend on the outcome of a battle between the Horati triplets from Rome and the Curiati triplets from Alba Longa, and both sets of triplets were of the same age. And in the battle, the three Curiati were wounded, but two of the Horati were killed. And the last Horati feigned flight and enticed the Curiati to pursue him. Now, because they were wounded, the Curiati became spread out, and this allowed Horatius to slay them one by one. And Victor argued that it is in Horatius that we find a real engineer, rather than face by full frontal assault the uneven odds of direct attack. Horatius chose to feign running away from the problem, thereby subdividing it into components that were individually tackled with ease. And he argued, Victor argued, that good engineering design is founded on the ability to make creative and ingenious decisions in the face of uncertainties, which minimize or avoid the uncertainties at reasonable cost. Then, in his lecture, if you read it, followed a fascinating discussion on the role of prediction in design. And this is very relevant today because with the modern emphasis on developing sophisticated methods of testing and of numerical modeling, there's an understandable tendency to believe that good design requires advanced analysis and prediction. Indeed, many undergraduates leave our schools of engineering believing that you cannot design something until you can analyze it. And in fact, Lamb, in his 1973 ranking lecture, emphasizes that prediction is at the very heart of the practice of civil engineering, and that one must not only predict, but make decisions and take actions on the basis of the predictions. Now, characteristically, Victor turned that approach on its head. He turned it upside down. And while accepting that prediction is a necessary vehicle for adequate decision, he pointed out that often our ability to predict what will happen is poor compared to our ability to predict what will not happen. Now that's typically Victor de Mello. And it's a profound statement. What it means is that wherever possible, good design should aim at avoiding reliance on precise predictions. It should aim at developing design solutions that cut across the uncertainties. And in 1971, I think Goldberg summed it up very nicely when he stated, any design that relies for its success on a precise calculation is a bad design. And then Victor set out a checklist of 5 design principles for embankment plans which aid decisions taken in the face of uncertainty. In doing so, he distinguished between mechanical behaviour, which results from an integration of average properties, and behaviour that is triggered by some sort of local phenomenon. And I took the liberty of generalising his 5 design principles to general engineering. I won't go through them in detail, but just going through them, design principle 1, I think, adds up to the need for robustness. And design principle 2, if possible, if you have a problem, change the problem. Design principle 3 emphasizes the importance of redundancy. And design principle 4 again brings out the importance of observational control. Finally, a very important design principle is to continually ask what if questions. Now, our president referred to meeting Victor de Mello, first of all, at the San Francisco conference. And there, in his presidential address, Victor made another challenging statement, which is very relevant to us today, and to which I believe we should all aspire. So I'll read it to you. I submit that the most important question facing the geotechnical engineer is for him to reassume position as the foundation instrument of every civil engineering orchestra, and for the civil engineer himself to reassume his position as the most influential element of human society in affecting the environment. What a challenge. There is so much to learn from Victor de Mello. And in conclusion, I believe that engineers of all disciplines, not just civil engineers, have a great deal to learn from this brilliant, inspiring and cultured man. And above all, we can take to heart his insistence that we are human beings first, engineers second, and specialists third. But the order is very, very important. So, ladies and gentlemen, that is a brief reflection of the first Victor de Mello lecture. And we now come to the event of the evening that we've all been waiting for, and that is the second Victor de Mello lecture. Extending over a period of perhaps 2 years, almost every email from Victor posed a number of probing, fundamental soil mechanics questions. And I have one of Harry's emails to Victor. I hope you'll forgive me for quoting this, because it says a lot about Harry, as well as saying a lot about Victor. So I quote, "Your resilience is remarkable. I'm sure that if I were in your situation, I would be highly unlikely to be contemplating the finer philosophical points of soil mechanics. I wish you well with your struggle against physical infirmity, and also with your equally daunting mental challenge to make sense of some aspects of our discipline." Harry knew Victor well, and in a few words, he had summed up our admiration for Victor's physical and mental tenacity and our concern for his physical health. I should have actually ended with that slide after my introduction, because it shows Victor, a human being, on a windsurfer. Now, Harry Poulos was born in Australia in April 1940. He went to the University of Sydney to study civil engineering and graduated with first-class honours in 1961. He stayed on to undertake research in soil mechanics under the inspired leadership of Professor Ted Davis. And then, after completing his PhD on three-dimensional settlement analysis, Harry had 9 months' experience with a firm of consulting engineers before returning to the university in 1965 as a lecturer. And he flourished under Ted Davis's leadership, and his progress was rapid. A senior lectureship in 1969 was followed by a readership in 1972 at the age of 32. And in 1981, Professor Davis died unexpectedly, and Harry found himself inheriting the leadership of the soil mechanics group, and a year later he was appointed to the chair of soil mechanics. So successful was he in that leadership role that in 1984 he was appointed head of the combined school of civil and mining engineering. He held that post with great distinction, together with that of director of the Centre of Geotechnical Research. He held that post until he joined the Coffee Group in 1989. And he went on to retain his formal links with the University of Sydney until 2001, spending a day a week at that university. During his time in academia, Harry's research output was, I can only describe as prodigious. He specialised in power foundation analysis and design, and he has made major contributions to our understanding of the way structures interact with the ground, which is one of the most challenging problems engineers face. And then, just as Harry moved into academic leadership with marked success, gaining the huge respect of his colleagues, so too did he move into leadership in professional practice, becoming Director of Advanced Technology at the Coffee Group in 1989, Chairman of Coffee Partners International Limited in 1991, held that post till 1993, and then he became Senior Principal of the company. And over the last 20 years in the Coffee Group, he has been an active and tireless geotechnical engineer whose unique skills in the field of foundations has elevated him to a position where he is regularly consulted by clients both in Australia and all over the world about hugely challenging geotechnical problems. And at the same time, he has attracted top-rate engineers to the Coffee Group and inspired them with his professionalism and his creativity. And in his dealings with staff, clients and colleagues, he has consistently displayed a level of integrity, of dignity and modesty that inspires trust and confidence. Professor Poulos has received numerous awards and honours. It would take me all evening to list them. But amongst those, the most notable are Fellow of the Australian Academy of Science, Fellow of the Australian Academy of Technological Sciences and Engineering, Member of the Order of Australia, the Centenary Medal of the Australian Government, and the Kevin Nash Gold Medal of the ISSMGE. And his most recent honour is his election as Distinguished Member of the American Society of Civil Engineers. And I think he and Maria are going to have a very enjoyable trip soon to the States for that award. He has delivered a number of the most distinguished lectures in the geotechnical calendar, including the 29th Rankin Lecture of the Institution of Civil Engineers, the Tazardi Lecture of the American Society of Civil Engineers, and the Tazardi Oration of ISSMGE. So, Mr. President, it is for me both an honour and a huge pleasure to invite Professor Harry Poulos to deliver the second Victor de Mello lecture.
Ladies and gentlemen, thank you very much, Professor Berlin, for those extremely kind remarks. I do appreciate it. let me say how honoured and privileged I feel to be invited to give this lecture, which is dedicated to a man who had a substantial influence on my career and on the geotechnical profession in general. I'm indebted to the Brazilian and the Portuguese societies for this kind invitation. Victor de Mello was a Brazilian by nationality, but in every sense a citizen of the world. And I'm going to follow on somewhat from John Berlin because I've tried to extract my perception of the essence of Victor de Mello and the influence that he has had on the profession subsequently. But let me define what I mean by legacy, firstly. And if we look in the dictionary, a legacy is something that's handed down from a predecessor or from the past. And I think an example of the use of that word legacy will encapsulate what I mean by the title of my lecture, the legacy of Victor de Mello. This is a legacy whose value the changes of time cannot affect. And I think John Berlin has said this, that Victor's influence will be everlasting in our profession. And that quote was from one of the novels by Joseph Conrad. And as John has said, Victor was no ordinary man. He was an engineer. Of course, he was a human being first. But an engineer, a philosopher, a polymath. He seemed to be able to converse on every subject with authority. He was a mentor to me and to many others, and a friend. And I must say that when I first met Victor de Mello, it was 1969, and he was giving a lecture that I will refer to very frequently in my lecture. And as a young academic at that time, to be recognised by this eminent gentleman was a great boost to me and to my career. And he, for the rest of our relationship, was always supportive and helped me a great deal. Just two photographs that I've been able to extract from Victor's one and only visit to Australia, and it was around about 1985, soon after he took over the presidency of the International Society. The photograph on the left is of Maria Luisa and Victor and my wife Maria overlooking the Pacific Ocean from one of the areas in Sydney. And the next photograph on the right is at a cocktail reception. The tall gentleman on the right-hand side is Dr. Peter Mitchell, who was the chairman of the Australian Geomechanics Society. Then there's Victor, and then there's another young person there who was me, I believe, and Maria Luisa. And so that was a great source of pleasure, and from that visit of Victor's, we learned a lot of what John has talked about, Victor's approach to engineering, and we actually learned a lot about Brazil, because unfortunately in Australia at that time, and possibly even now, we tend to be rather ignorant of this wonderful country. The outline of this thesis is as follows. I want to just perhaps build a little bit on what John has said about the de Mello philosophy, and how that then relates to four particular issues which I've extracted and are relevant to foundation engineering. The first is the principles of design, then shallow foundations and the estimation of bearing capacity of shallow foundations, then the axial capacity of single piles, and finally I want to say quite a bit about settlement reducing piles and pile drums, because I believe that the paper that was co-authored by Berlin, Broms and de Mello was a landmark paper in foundation engineering, and one that I still refer to very frequently. This is, and I was unaware of the repetition here, these are the aspects of the de Mello philosophy that John Berlin just told us. Robustness, changing the problem, redundancy, observational control, and ask what-if questions. And again, I think that last one, certainly in design, is very important, that because of the uncertainties that prevail in geotechnical engineering, we must ask what-if questions. What if we're incorrect in our assessment of stiffness or strength? What effect will that have on our design, and how can we allow for the inevitable uncertainties in our design process? Coming firstly to design criteria, I quote from Victor in 1995, and he said at that time, of the many absurdities in design practices, one lies in requiring the same factor of safety per pile, whether it is alone in supporting a column or is one of a group in that task. And this is a philosophy that I believe also Professor Berlin shares, that there is not a logical approach in a lot of the current design processes. And Victor was really quite concerned about that. He was concerned about the unthinking acceptance of the provisions of codes and standards that contain excessively conservative assumptions or are not consistent with practical experience. He was concerned about a lack of rationality of foundation design methods. He was concerned about ad hoc choices that designers make for the factor of safety against failure. And in trying to follow de Mello's concerns, I've been involved for a number of years with the piling code in Australia. It's an Australian standard, so it has legal status. And I and my colleagues shared the same concerns as Victor de Mello. And what we've tried to do there is to follow some of the de Mello principles, to reduce the ad hoc judgments involved in selecting safety margins, to consider the risks involved more specifically, rather than just plucking numbers off a table or out of our heads, to provide some incentive for doing pile testing, because there is a resistance, at least in my country, to doing pile testing. And also, and this was quite apparent from the quote I showed you just now, to allow for the benefits of redundant foundation systems. In Australia, we adopt the limit state design approach, and for ultimate strength, we require that the design geotechnical strength equals or exceeds what is termed the design action effect, or putting that in English, the factored down strength geotechnical capacity of the pile needs to be greater than the factored up loads. And in order to get that design geotechnical strength or capacity, we make our best estimate of the ultimate capacity, and then we apply a reduction factor, which I call 5G, to that. Now, what we tried to do here was to apply a more rational process to the selection or the assessment of that reduction factor 5G. And so the equation that I have here, and I don't want to go too much into detail, but it involves three components. One is a basic reduction factor, another one is what we call an intrinsic test factor, and then there's a testing benefit factor. And the first thing we look at is the basic geotechnical reduction factor. And that depends on assessing the risk factors and weighting those risks. And the broad factors that are considered are firstly the site factors, then the design factors, and then the installation factors. We then have a number of factors for design, including experience in similar conditions, the method of assessing the design parameters, the design method, and the method of getting the test, or how we interpret the test results. And what you'll notice there is that we assign a weighting factor of 2 to the method of design parameters and how we interpret the test results, but the design method is only weighted as 1. And I think this follows on from what John Berland has said. It's much more important to get your model right than to try and use a very sophisticated method. You can get very bad answers by using very sophisticated methods. And in terms of installation, we look at the level of control during the installation and the performance monitoring during and after the construction of the pilot. Now, for each of those risk factors, we, as the design engineer, apply our judgment and assess a risk rating which ranges from 1 for a very low risk that we assess to 5 for a very high risk. And so we do all of this, we use a spreadsheet, and we then put all those risk ratings together and arrive at an average risk rating for our particular foundation on our particular site. And it's by summing up each individual risk factor and weighting it. And then we've used reliability theory in an approximate way to relate that average risk rating then to the basic geotechnical reduction factor. And you can see that, oops, sorry. Let me now turn to another issue that concerned Victor de Mello. And he expressed some skepticism in 1969 on the validity of conventional bearing capacity equations. And he said the theoretical solutions to the problems are still subject to discussion, both in comparison between them, because there was quite a disparity in some of the solutions theoretically, and in comparison with control tests designed to check their validity. In other words, Victor was questioning the Terzaghi bearing capacity theory that appears in every textbook that has been written on foundation engineering. And indeed, I think time has indicated that Victor's skepticism was well-founded. And I just want to highlight 2 issues here which depart from the traditional bearing capacity theory. The first of these is the effect of the compressibility of the soil. And this was an issue that the late Professor Alex Bessich identified in the early 1970s, just after Victor de Mello's lecture, and it showed, the work that Bessich showed, that showed that the bearing capacity actually decreases with increasing soil compressibility. So we had a situation that was a little bit unusual for geotechnical engineers in that compressibility and strength were actually interlinked, although of course this was recognised some time before by many other people. And classical theory of bearing capacity using rigid plasticity doesn't take that into account. And I was involved in a number of tests and quite a deal of research in the 1980s on the capacity, the bearing capacity and the axial load capacity of piles in calcareous sands, because these were very relevant to offshore projects that I was involved with at that time. And what this left-hand diagram shows is on the vertical axis the applied loading or pressure on a model footing, and on the horizontal axis the settlement. And the upper curve is for a normal silica sand, a normal quartz sand, and the lower curve is for a carbonate sand. Now, if you do the normal type of tests, the carbonate sand has a friction angle of about 45 degrees. The silica sand has a friction angle of about 38 degrees. So according to Terzaghi's rigid plastic theory, the carbonate sand should have a much greater bearing capacity than the silica sand, but that isn't the case. In fact, the carbonate sand has about 1/3 of the capacity, and the reason is that it is much more compressible than the silica sand. The graph on the right-hand side just shows the variation in bearing capacity as a function of the relative density of the soil. And if we just look at how the various theories and the experiments line up in these two diagrams, the diagram on the left is for silica sand. It shows how the bearing capacity on the vertical axis changes with the overburden pressure. And the theory of Terzaghi shows that you have a huge increase in bearing capacity as your overburden increases, and the test results don't show that. And cavity expansion theory and other theories that take account of compressibility, and indeed the theory that Terzaghi called local shear, where you reduce the friction angle by 1/3, gives a much better agreement than the rigid plastic theory. The left-hand diagram is for silica sand, the right-hand diagram is for carbonate sand. So Victor de Mello's questioning of conventional bearing capacity theory was indeed quite justified, because if you apply bearing capacity theory traditionally to carbonate sands, you would seriously overestimate the capacity of foundations on that sand. And indeed, this is what happened, and this is what led to some of this research. The second issue I just want to discuss briefly is the effect of footing size as displayed by the conventional theory. And if we look at the component of bearing capacity in the Terzaghi equations, that is the n gamma term as we call it, it has a factor B, the width or size of the footing involved in it. So according to this theory, the bigger we make the footing, the bigger is the bearing capacity. Well, unfortunately, this is not borne out by practice, and it's good that we have Professor Brio here, our president of the International Society, because in 1994 he hosted a prediction symposium where he, on his university test site, carried out a series of tests on various sizes of footing and got a number of people to predict the behaviour. And one of the interesting outcomes of that test, and this was something that Professor Luciano de Cor picked up on and reinterpreted those tests, when you plot ultimate pressure on the horizontal axis on this right-hand diagram against settlement or relative settlement, you actually get a unique line. And this is not what Terzaghi's bearing capacity says. You should get increasing pressures as the footing size increases. And quite recently, another paper that was published by Gavin and his co-workers came to the same conclusion. And I think early this year, another paper also by Paul Howie and his colleagues at Cornell showed a similar thing. So, basically, the experimental evidence, both from the field and from laboratory data, indicates that the validity of the size-dependent component of the bearing capacity of footings on sand has to be seriously questioned. And I think we really need to re-examine the way that we estimate the bearing capacity of foundations, particularly on sands, where this size effect is theoretically quite significant. Let me now move on to the axial load capacity of piles. And in his state-of-the-art lecture in 1969, again, de Mello, in his characteristic fashion, questioned the status quo. He questioned the methods of capacity estimation. Were they adequate? He questioned whether the displacements to failure were dependent on diameter or diameter independent with respect to the shaft and the base. He questioned whether there was indeed a limiting shaft friction with depth, because some of the recent work that had been published at that time indicated that perhaps the shaft friction along the pile became constant with depth. He also questioned the relationship between skin friction in tension and compression, and he questioned the status of our load settlement prediction capabilities. And if we look at the capacity estimation methods then and even now, I think they can be classified into 5 categories: those that involve total stress, those that involve consideration of effective stress, and then methods where we use in one way or another in situ test data, such as the standard penetration test, the SPT, cone penetration test, CPT, and the pressure meter test, PMT. Now there's a very recent study, this was published in December of last year in the American Society of Civil Engineers, Geotechnical and Geoenvironmental Journal, and it's an interesting study on the measured and calculated shaft capacities and base capacities of an H-pile in sand. And what the authors did was to take a number of methods that are available in the literature, and these methods include a couple of methods, in fact, from Brazil by Aoki and his colleagues, and also include some quite modern methods which make use of the cone penetration test. Interestingly, the measured capacity there was about 1100 kilonewtons of that H-pile. The calculations based on the various methods range from about 600 to about 1700 kilonewtons, almost a factor of 3. This is 2009, a fairly straightforward problem. So this isn't particularly heartening. The base capacity wasn't quite as variable, depending on which methods they used, but there was still a concerning lack of consistency among the different methods. So the disturbing inference that we draw from studies such as this, and this is not an isolated study, it's been found consistently over the 40 or 50 years since de Mello wrote his paper. We have difficulty in accurately predicting pile shaft capacity. Why is this so? Well, clearly in an actual situation, the effects of the construction technique and imperfections that arise during construction can have a major effect. But beyond that, quite often we tend to use inappropriate correlations. We look for some correlation, some authority that says the skin friction is related to SPT. You look up a book or a paper and you take it and you don't read the accompanying statements which say be careful because this may only apply to certain soils. And also, I think something that we tend to overlook, but is, in my experience, extremely influential and important, and that is the application of judgment. Each of us, when faced with a particular problem, will have to idealize that problem and convert it to something that we can calculate. And I've done this with my students on many occasions. I've given them a single set of data. I've told them this is the method you should use, and I've got them to predict the capacity of a footing or a pile, and quite often you get differences of a factor of 2. Same data, same method. What's different? The perception of the engineer or the student. One would hope that students are rather more variable than practicing engineers, but regrettably this isn't always the case. I just want to take up one other point that de Mello raised, and that is the difference between shaft capacity in uplift and compression. And there had been, at that time, 1969, some conflicting evidence, particularly in relation to piles and sand. And I think the situation, at least for me, was clarified substantially by the work of De Nicola and Randolph in 1993. And they identified that one of the key issues that may affect the uplift versus compression capacity is the compressibility of the pile relative to the surrounding soil. Because if you have a very compressible pile and you load it in compression, the pile will actually push out and will increase the lateral stress on the interfaces, so tend to increase the skin friction. However, if that very compressible pile is pulled, then its diameter will contract, the lateral stress will reduce, and so your skin friction tension will be less than in compression. And the more compressible that pile is, or the stiffer the ground is, the greater the difference between uplift and compression capacities. And so certainly in my company now, as standard practice, we use these sorts of relationships between the reduction of capacity in uplift versus compression versus the relative compressibility. And that's now standard practice. Load settlement estimation, there have been many developments. Since 1969, we've seen the refinement of load transfer methods, we've seen the development of boundary element analyses, we've seen the development of finite element analyses, and we've also seen other adaptations of simpler approaches, modified elastic solutions. And I don't want to spend too much time on this, but let me just point out one of these modifications that I believe has some potential for practical application. And this is the work of Professor Paul Main at Georgia Tech in the United States. And what Main has done is simply to hypothesize that the stiffness of the ground surrounding the soil bears a sort of hyperbolic, a power relationship with the load level acting on the pile. And so you finish up then with a curved load settlement relationship based, the initial stiffness is based on a small strain modulus and elastic theory, but that small strain modulus then degrades with increasing stress level. So it's an extremely simple approach to use, but it actually, according to Main, gives you remarkably good agreement. And you don't have to do finite elements, all you have to do is to have a little chart and just use it that way. I want to now move on to the last subject that I want to discuss in the legacy of Victor de Mello. And that's the issue of settlement reducing piles. And Professor Berlin mentioned this paper, and I believe it's a highly influential paper. It focuses on settlement rather than capacity. And this, in 1977, was quite a revolutionary approach. And even some people today would say it's revolutionary because capacity for many people is first thing. But there's been a great deal of research in this area since 1977, some of it here in Brazil, some of it in Japan, in Germany, many other countries have embraced the concept of using settlement reducing piles. Regrettably, the concepts involved are not universally embraced in all countries. And there are still some countries, some advanced countries, that will not allow the use of settlement reducing piles because their codes say that as soon as you put a pile in the ground, each and every pile has to have a factor of safety of 2.5 or more. And this, of course, is what Victor de Mello said was a stupid principle, and he was right. The design issues, when we come to looking at the design of settlement-reducing piles or pile drafts, we of course do have to consider the ultimate capacity under both vertical and horizontal and moment loadings. We have to look at differential settlements and maximum settlements because these often are the key issues in design. The design revolves not so much around capacity, but in terms of controlling the serviceability of the foundation structure system. And then we have to recognise that not only do we have to do a geotechnical design, but we also have to do a structural design because we have to satisfy structural as well as geotechnical requirements. So we need to be able to compute the moments and the shears in the raft and the loads and moments in our piles. I don't want to go into the methods of analysis that we employ, because that could take one or more lectures by itself. But let me just point out one or two key issues, I think, with respect to the characteristics of pile graphs. The diagrams here are taken from a paper by Mandolini and his colleagues in Italy, and what they did was they analysed a foundation that had been constructed and designed as a conventional pile foundation supporting a major bridge. And that foundation involved the use of 144 piles. What Mandolini did was that they re-examined that foundation system and looked at the relative settlement. That's relative to a foundation with no piles as a function of the number of piles on the horizontal axis. Now what they found, and this is what we found quite consistently, is that as you increase the number of piles, you of course decrease the settlement, but only up to a certain point. Now once you go beyond that point, you basically have formed a block, and a block can't be more of a block than a block. And so there is a law of diminishing returns. So there's an optimum number of piles beyond which you get little or no benefit by increasing the number of piles. And in this particular case, they found that that limit was almost exactly at half the number of piles that were actually used in this foundation. So had this foundation been designed on the basis of the piles being settlement-reducing piles, they would have used half the number of piles. The other thing about pile graphs is that you can be smart in design. And too often we're not smart in design. We say that we may need 25 piles, as in this hypothetical example by these two authors here. Now, our normal method would be to have then a 5 by 5 rectangular arrangement of piles. But if we do that, we finish up with a situation in this particular case where we have quite significant differential settlements. A maximum settlement at the middle here and much smaller minimum settlements at the edges. If we rearrange those piles so that we have the stiffness of the foundation where we need it, which is in this case in the middle of the foundation, and less piles out of the side where we don't need them, then we can actually get an almost uniform settlement. So just by thinking about the problem, we can get a much more satisfactory outcome without any additional cost. And there are a number of examples, and I'll very quickly go through these. This is one of Professor Hansbo's examples from Sweden, where he had two buildings, one on 211 piles, the other one on 104 piles. The 104 piles was designed on the basis of settlement-reducing piles, so that the factor of safety, if you like to think of it that way, of the piles was of the order of 1.3 or 1.4. The first house had 211 piles, was designed as a conventional pile system. Measurements were taken at the time settlement behaviour of each of those houses. They had similar loadings, and in fact the settlement was very, very similar. So the house number 2 on half the number of piles, in fact, showed slightly less settlement than the house number 1 on 211 piles. Another example of how we've probably got far more piles in the ground than we need to have. And I don't want to upset any of the piling contractors here, but you've probably benefited greatly from some of the designs that have gone on. We've actually been approached by piling contractors in Australia because they see the potential benefit when they're bidding for projects of being able to reduce the number of piles and outbid or underbid their competitors. So we had, for example, on the Gold Coast in Queensland in Australia, a 30-storey tower. The original design required 140 on piles 35 to 40 metres long to rock. The revised design used 123 CFA piles, and they didn't go to rock. They're about half as long, so we saved nearly 3 kilometres of piling and about $500,000. And the settlements were about 5 millimetres different only, and quite within acceptable limits. And another building in the same area, 23-storey building, the original design, and this was a structural engineer's design, 437 piles to rock. Our design, 232 piles to rock, taking account of the raft. Again, we saved about $500,000 on that particular job. And in fact, we improved the settlement performance because we were able to reduce the differential settlements. Very briefly, I'll just say something about the Burj Khalifa in Dubai, which is now the tallest building in the world and is founded on a piled raft. And it was designed as a piled raft, although not as bold as some of the other structures. But that building, as I think many of you will know, is 828 metres tall. The foundation system under the tower itself consists of 196 board piles, 1.5 metres in diameter, extending 45 to 50 metres below the base of the raft. And then outside that, we have a podium area with 750 piles, but much smaller and all the way below. So we were involved with Hyder with the designers, we were the geotechnical peer reviewers, and we did predictions independently of the settlement of the tower with this foundation system. Both Hyder and ourselves got very similar results. And here are some measurements, settlement contours taken now a year and a half ago or more, showing a very symmetrical arrangement of settlement. The raft itself was 3.7 metres thick, so it seems to be quite a thick raft. But in fact, the differential settlements are still there, so that in the middle you get a maximum settlement and you get a minimum settlement out here. The differential settlements at this stage were about 20 to 25 millimetres. The predictions, our final prediction is shown on the bottom line here. That's the predicted settlement profile on one of the arms of the tripod of the foundation system. These are measurements of settlement at different times during construction. So we predicted a final settlement of the order of 75, 76 millimetres. The maximum settlement when the tower was almost complete was about 44 millimetres, and so our estimate is over the fullness of time that tower will settle of the order of 50 to 60 millimetres. And just to keep that 50 or 60 millimetres in perspective, the building itself is predicted to shorten by 300 millimetres because of the self-weight over the next 50 years. So geotechnically we're moving that much, structurally they're moving that much. So geotechnical wins. Just a few pictures of the progress of construction. That's the completed raft, and these are various stages during the construction. And that's the finished building. I think many of you will have seen the quite spectacular opening on the 4th of January, where the building that was previously called the Burj Dubai became the Burj Khalifa. And so it's quite a spectacular building. It may be unnecessary, but it certainly is spectacular. I just want to say something about a subject that is not particularly well researched or understood, and that's the issue of piled rafts and soft clays. We know from experience that piled rafts are a very effective solution in situations where we have quite good ground conditions, where we can get quite a lot of stiffness and capacity from the raft. And that happens in places like Frankfurt, where they have stiff clay. It happens in the Middle East, where they have cemented sands and carbonated sands. It happens where you've got sandy
dense materials. But with soft clays, people tend not to think about pile drafts. But in fact, we can, if we're faced with this sort of problem, get some benefits by considering the possibility of using pile drafts. We have to, however, recognise that when we're dealing with piles in soft clay or foundations in soft clay, we must be prepared to accept settlements that are larger than the 25 to 50 millimetres that sometimes we're asked to try and achieve. What we must remember with foundations, particularly pile foundations, pile raft foundations and soft clays, is that in many situations the soft clay may well be settling because of previous reclamation or groundwater disturbances. And if you've got friction piles, then the friction piles will tend to move with the ground. If you've got end-bearing piles, then the end-bearing piles will tend to hold still, the ground will move around it, and you'll finish up with quite substantial differential settlements. And we've seen this in so many places. Mexico City, of course, where the piled parts are sticking up and the non-piled parts are going down. So it's not always necessarily a good idea to try and completely stop or eliminate sediment. Sometimes it's better to do a foundation design where the whole system tries to accommodate to what nature wants to do, which is to cause the ground to settle. Another issue that I think is worth recalling is that we can use compensated pile drafts. These are pile drafts where we undertake an excavation, and often we have to do this anyway in order to construct basements, and then we can build a pile draft in that excavation and build our structure out of it. Now, when we do this, we need to consider, of course, the maximum depth of excavation, how we're going to hold that excavation open. We need to look at the effects of the excavation on the capacity and stiffness of the raft, and also on the pile capacity and stiffness. And one of the interesting things we find is that when you excavate in soft clay, which may be normally consolidated, you release stress, and so the clay actually then becomes over-consolidated, and so when you reload it, it is much bigger than it was on first loading. And so what happens is, in fact, that when the raft contacts that excavated area, initially the ground will behave in a reasonably stiff manner until we basically overcome that compensation pressure, and then it starts to behave as a normally consolidated clay again. But that effect may be enough to reduce the settlement down to an acceptable amount. And we can also, in this sort of design, allow for the effect of ground settlement, so that we can, with an intelligent design, try and get the building to settle more or less the same amount as the ground. And I won't go into the details there, they will be in the written paper. We must recall that this principle is not new. It was applied very successfully more than 50 years ago by Professor Leonardo Zayda with the Azteca Tower in Mexico City, where he used this concept of a compensated pile draft. He didn't call it that, but that's what it was. And it's a very interesting case study. We go back to the 1957 International Conference in London for the details. But what we've done is we've tried to go back and re-examine that case history using what information was in Zaydak's paper. And so this table tries to summarise in the middle column the predicted settlements. And the first one is if the raft alone was supporting the building, and it would settle nearly 3 metres or 2.3 metres. If we have a compensated raft, then the settlement reduces substantially to something of the order of
900 or so millimeters. If we use a pile draft without the excavation, we would get a settlement of the order of 1,000 millimeters or so. But the compensated pile draft, we calculate, settles about 280 millimeters or so. So the numbers on the right-hand column show the relative settlement relative to a raft with compensation. And it's interesting that in the settlement measurements that Zabart presented in his paper, the settlement at the end of the measuring period, when it was basically creeping, was of the order of 210 to 220 millimeters. So reasonably consistent with the predicted final settlement. And Dr. Salas did an analysis of this and compared it with what was actually measured. And again, I won't go into too much detail, but the left-hand side shows the settlement versus time on the horizontal axis, settlement on the vertical axis. The dots are measured settlements, and we had two alternative soil profiles or models that we used that are shown in the full lines. And the agreement is quite reasonable there. What's very interesting here is the right-hand diagram, which shows the proportion of load, or the load that is carried by the raft and the piles as a function of time. And it's interesting that in the early stages of construction, the raft actually takes most of the load. And this is consistent with our hypothesis that after the excavation, when you build the building on a compensated pile raft, the ground underneath the raft is stiffer than it was before, and so it tends to take rather more of the load than it would otherwise. And of course, as the load increases, the piles take an increasing amount of load. But that's a foundation design where there's a significant proportion of the load is in fact carried by the raft. And I just want to show you very quickly some cases of pile rafts in Malaysia that have been built on very soft clays. These are residential buildings, so they're not spectacular, they're not the Burj Khalifa and so on. They're 2- and 5-story residential building developments. But there's a lot of money involved because there's a lot of buildings involved. These aren't my projects, so I'm indebted to Dr. Gui and Dr. Tan from Malaysia for this information. But in the designs that they have developed, they've used pile rafts, they haven't used compensated pile rafts. These are the sort of ground conditions, and I won't try and go through there, but let me just tell you that the ground is very soft and compressible. This is the undrained shear strength, so typically something of the order of 10 to 15 kilopascals near the surface, and it increases linearly with depth. So it's pretty normally consolidated. And what they've done is that with the 2-story buildings, they've used a fairly conventional pile draft system. They've actually got ground beams that are deeper, and the piles then are founded on those ground beams. These are the actual houses completed. And the settlements that they've obtained, and they're only, these are during construction, and I think they didn't take any post-construction measurements, but the maximum settlements they got with those 2-story buildings were only the order of 20 millimetres or so. Certainly a lot less than you would anticipate with a shallow foundation. With the 5-story buildings, they've used this quite a nice approach where they've put longer and stiffer piles near the middle of the building complex and shorter piles on the outside where we don't actually need the stiffness so much. These are just a few pictures of the construction, of the excavation, and the reinforcement for the beams and the concrete. And here are the completed 5-story buildings. And these are the measured settlements. These are significantly larger. They're of the order of 60 to 70 millimetres maximum, but that's not unacceptable if you design for it in terms of the surface. We also did an analysis of these particular buildings, looking at what would happen if you just had shallow footings and then you used piles without taking account of the raft. And we found that we would predict, therefore, the two-storey buildings, a maximum settlement of the order of 43 or so millimetres, and the measured settlements at the end of construction were somewhere between 8 and 22 millimetres, but continuing, so that I think that 40-odd millimetre prediction is probably reasonable. And for the 5-storey buildings, our prediction of the final settlement was just under 100 millimetres, and they'd achieved between 58 and 78 millimetres. So I believe that there is a potential for using the concept of pile drafts and settlement-producing piles, even in these sort of unfavourable ground conditions. We can get value for money. Let me make some concluding remarks now. And this was, I think, almost a cry of despair from Victor de Mello in 1995. Quo vadis geotechnica? Where is geotechnics heading? Basically, he was questioning, why haven't we improved significantly our predictive capabilities despite the great advances in numerical analysis and field techniques? And I think we can probably identify a number of obstructions to progress. And this is not an exhaustive list. Shortcomings in education. I think a lot of our geotechnical education, certainly in my country, has been reduced because of the demands of other disciplines within civil engineering. And I think some places tend to use outdated approaches in their teaching, and these then tend to get carried on by the graduates in their profession. There is inevitably a difficulty in obtaining adequate ground investigation data and a difficulty in estimating appropriate soil and rock parameters. There's a difficulty in the continued use of outdated methods, despite the fact that they've been shown to be inaccurate. And I think, and forgive me to the academics in the audience for saying this, but there's been a problem with the academic publishing imperative. In other words, academics, like it or not, are forced to publish in order to advance. Now, what this means is that they then have to try and do something new or something that hasn't been done before, instead of perhaps what really the profession may benefit more from, which is to go back and re-examine some of the techniques that we're using and try and assess, in the light of modern research, how adequate or inadequate those methods are. What have we done? Well, I quote from Rudolf Steiner, the well-known Austrian educator and philosopher, who said, "We're slaves of the past, but masters of the future." And we want to be masters of the future. So what can we do? Well, certainly we can improve the education of our profession. We can incorporate relevant modern research into our teaching. We can direct students to read the writings of the geotechnical gurus. And I think there's a lot of wisdom and guidance, and John Berlin mentioned this with respect to Victor de Mello's works, to be rediscovered. And I think some of our emerging academics would really benefit by sitting down and reading de Mello, reading Skempton, reading Peck, reading Terzaghi in the original, to see the thoughts that they have, because they're still relevant. And I think in terms of the profession, there should be refresher courses that are mandatory for practitioners, because some practitioners have been out of universities for many years. They still use the techniques that they're they used 30, 40 years ago. That may be okay, but maybe not. And I think refresher courses perhaps wouldn't be a bad idea. Better practice, I think we need to focus more research on assessing the theory and closing the academic or the theory practice gap, because there is a gap. I think we can abandon some of the old methods that still persist. They were convenient 30 years ago. They're not really relevant now. And one of the important things is that we need to make a push for better ground characterization. We need to be using modern techniques. And I know Paul Main, when he talks to audiences, shows the difference between a 1904 car and a 2004 car. Huge amount of difference. A 1904 SPT and a 2004 SPT, the same instrument basically. So we need to get updated with our techniques, and really that is very important. And we should economize. We should recognize that ground investigation is not a cost, it's an investment. And we need to try and convince our clients that this is the case. In 1985, de Mello said, engineering uses art and science, intuition, and of course the rational analysis of the day. All these are means. Engineering is the end product of design, construction, and operation, a live function to be reviewed and revised. And I think this really sums up Victor de Mello. The process of review, of questioning, of revising concepts was evident at the end of his life as it was during his professional career when he wrote that state-of-the-art paper in 1969. And I think those of you who are privileged to be able to read Portuguese and to access the de Mello website can see in the unfinished manuscript of his text the thoughts coming in here, the questioning of the fundamentals. So ladies and gentlemen, let's be inspired by the example of this unique person, Victor de Mello, and let's not continue to be slaves of the past, but rather direct our energies to being masters of the geotechnical future. Obrigado.
Nosso agradecimento especial ao palestrante Harry Poulos.
Convido a neta do professor Victor de Mello, Maria de Mello, para entregar a medalha comemorativa ao professor Harry Poulos. Convido a esposa do professor de Mello e os filhos, a Lúcia e o colega Luiz Guilherme, para receber a homenagem da ABMS à família de Mello. A família de Mello, a Associação Brasileira de Mecânica do Solo de Engenharia Geotécnica, manifesta sua profunda gratidão e reconhecimento ao professor Victor de Mello por sua dedicação, contribuição e liderança enriquecedora para a comunidade geotécnica e para a sociedade brasileira.
Eu queria falar duas palavrinhas. Eu estou terminando de fazer a edição de menos trabalho que ele tinha escrito em inglês, pertinente ao mesmo livro, e vai estar disponível, creio que em coisa de um mês na website. E um colega muito próximo me pediu que falasse outra vez, que lesse um poema que meu pai gostava muito de falar em público, creio que vários de vocês ouviram no passado. Eu vou tentar fazê-lo. é um pedaço de um poema chamado Caminhante, de Antônio Machado. E ele diz: caminhante, são teus passos o caminho e nada mais. Caminhante, não há caminho, faz-se o caminho ao andar. Ao andar, faz-se o caminho, e ao olhar-se para trás, vê-se a senda que jamais se há de voltar a pisar. Caminhante, não há caminho, somente pegadas no mar. Obrigado.